This work introduced a novel depth-aware generative adversary network for talking head video generation. For talking head generation, it aims to produce a synthetic human face video that contains the identity and pose information respectively from a given source image and a given video. Rapid progress has been achieved on talking head video generation in terms of both quality and robustness in recent years. The first-order motion method is one of the most popular approaches in this field. Existing works for this task heavily rely on 2D representations. However, dense 3D facial geometry is extremely important for this task, as it is particularly beneficial for us to generate accurate 3D facial structures. Nevertheless, dense 3D geometry annotations are costly for videos and are typically not available for these video generation tasks. We are the first to introduce a self-supervised learning method to recover explicit dense 3D geometry from face videos for talking head video generation. We also propose a framework cooperative with DepthMap to adjust the talking head generation. Our method can produce better results compared with the existing methods. We first introduced a self-supervised geometry learning method to automatically recover the dense 3D geometry from the face videos without the requirement of any expensive 3D annotation data. Based on the learned dense depth maps, we further use depth maps to estimate sparse facial key points that capture critical movement of the human head. In a more dense way, the depth is also utilized to learn 3D aware closed model attention to refine the generation results. In the self-supervised face depth learning module, we reconstruct the target view using the estimated depth map, the source view, and the camera metric by equation 3. Thus, we can learn a satisfied face depth network by the reconstruction loss. After we obtain the depth map from the face depth network, we adopt a feature warping strategy to capture head movements between the source and the target images. Importantly, we predict a motion flow mask and an occlusion map in this module. The motion flow mask assigns different confidence values for the estimated dense 2D motion field, while the occlusion map aims to mark out the feature map regions that should be impinging since the head has variant rotations. To effectively embed the learned depth map to boost the generation in a more dense way, we propose a closed model attention mechanism to enable the model to better preserve the facial structure and generate for expression-related microfacial movements, as the depth can provide us dense 3D geometry, which is essentially beneficial for maintaining the facial structure and identifying the critical movements. We first show recovered depth maps for human face from the proposed face depth network. We visualize the learned face depth maps and their corresponding 3D poise close. The learned dense 3D facial structure are clearly very beneficial and lead to a significant improvement on the generation. Additionally, we visualize the dense depth-aware attention maps. The high activation areas of each query point are mainly located in the expression-related parts of the human face. These visualization results indicate that our design closed model attention module can indeed adjust the micro movements of the human face to produce more vivid expression in generation. Also, from the qualitative comparisons with other methods, it can be observed that our DAGAN achieves the best result among all the compared methods. We conduct operation studies to demonstrate the effectiveness of components of our framework. Here, we also show some video samples to verify our method. We can also apply our method on cartoon images, and it can still perform good results. That's all. Thanks.